Tonight I'd like to talk to you a little bit about linear assumptions in a nonlinear world. It's interesting as we go through life, our biblical life of course, but also life in general, how we are constantly the victims of assumptions and presuppositions. Now you've heard me talk many times, some depth, about our false conceptions about the time dimension. How time, we always presume it's linear and absolute. We've talked about this whole idea that time is not absolute nor linear. In fact, time varies with mass, acceleration, and gravity. Not that we want to make this a physics lesson, but it turns out that if you understand that time is a physical property, it suddenly clarifies all kinds of apparent paradoxes in the Bible. The fate versus free will, our freedom, our choice versus predestination. All those issues are problems only because we view them from within the dimension of time rather than to transcend time as God does. And we've talked about that, and there are some further discussions, though, that I'd like to get into that have to do with fallacies in our thinking. In this case, the fallacies I'd like to deal with affect not only your philosophical or theological or biblical horizon, but also your practical everyday life. We tend, intrinsically, as human beings, to make linear assumptions about almost everything. We tend to presume that what was true today will be true tomorrow. Things that we relied on in the last few years, we can rely on tomorrow and on. We tend to make linear assumptions. And yet, if we do any thinking about it at all, we realize our world, the real world you and I live in, is very nonlinear. It's not at all uniform. It's not at all smooth. Mathematicians will use the term linear and nonlinear, and it's a very descriptive phrase. For example, let me give you an example of some nonlinearities that affect us. One kind of nonlinearity are earthquakes. I assume you've noticed a few lately. A couple of years ago, we discovered that our home at Big Bear was on an epicenter of the Big Bear quakes. 4,500 homes destroyed or damaged. No one hurt in that one. And of course, that led to us that was the Lord's way of getting us open to a relocation, which we were not until that happened. And of course, as you know, He's led us to Idaho. Tragically, of course, many, many people have been hurt very badly by the earthquakes in the region. But I mention that whether they're earthquakes or other natural calamities, floods in the Midwest, hurricanes in southern Florida, whatever, there are nonlinearities in our life. And we don't call them that, yet we should recognize they do occur. Don't expect them. Some kinds we sort of take insurance against, and yet we never really expect them, and yet they do come. Nonlinearities of all kinds. Those are natural. There's also political nonlinearities. The great empires of the past, we read about in the Bible, whether it's Egypt, Assyria, Babylon, Persia, Greece, Rome. We study those. Those were all forms of discontinuities. It's interesting if you do have any history of the Roman era. The one thing that the leadership and also the population within the Roman Empire were sure of, they may not have approved of their empire, but they took for granted that it would last forever. The idioms in their literature and their whole way of life was the presumption that because of its power, it would be there forever. It's kind of interesting that if increased taxes and lavish spending could repair an economy, Rome would still rule the world. You can take that where you want to. Even cycles, by the way, economic cycles, recessions, even though they're cycles, that implies linearity. Linearity is a mathematical term, meaning it's, in a sense, predictability. We use the expression in our life, the straw that broke the camel's back. It's sort of a way of expressing the fact that circumstances can occur in every mode of our existence that cause disruption, nonlinearities. It's interesting to me, one reason I started to get into this is because we're seeing major nonlinearities even in our sciences. The field of physics, which has classically been the hardest of the hard sciences. Physics has always had the advantage of having empirical physicists audit the theoretical physicist. The theoretical physicists could come up with some concept, but in the field of physics in general, you could conduct experiments to prove or disprove the theory, and so the field of physics has had a fairly steady course of solidarity. It's been one of the more solid of the sciences, where many other sciences were denied the ability to do empirical verification. Physics has always enjoyed that, and as a result has had an unusual history. And yet, in the field of physics, they are now confronted continually with what they call nonlinearities. The best example, of course, is this whole business of the Big Bang, the fact that they now discover that the universe is finite, not infinite. That points to the fact that it had a beginning. So even within the idioms of physics, they're facing the fact that there's a boundary condition where it all started. Not only mass and energy, but time and space. And we've talked about that in the past. The whole concept of black holes is an example of that, where a star can collapse, and as it collapses, it becomes more dense. As it becomes more dense, its gravity increases. As the gravity increases, it becomes more dense. It finally contracts to a neutron star. If it's of a certain mass size, it's a little larger. It can contract so far that even light cannot escape. And in fact, it even cuts itself off from our time domain. And so the whole area of the black holes and the Schwarzschild shield radius and all that stuff is of course something that we now can confront. Perhaps even more provocative is the field of quantum physics, where in the field of quantum physics they discover now, in the particle physics, there's some bizarre confrontations going on, because we now know that there are units of length that cannot be subdivided. You always think no matter what length you have, you could cut it in half. That's not true. In quantum physics, there's a limit to how small a length you can deal in. So that's why they call it quantum. Units of length, units of mass, units of energy are discrete elements. They're really digital in effect. What's perhaps most bizarre is that the unit of time itself has an indivisible, a point at which you can no longer divide it, which is strange. And that leads to a whole philosophical construct that's too bizarre for us to even get into tonight. In fact, it's so bizarre that I plan to do a special series just on that issue. And of course, the field of cosmology, the Big Bang is a discontinuity, of course. Non-uniform issue. We've talked in that area about the anthropic principle, the fact that as we study the universe, we discover it's been designed. In fact, there are nonlinearities required in the design. Very strange. The example is water. Everything expands when it gets warmer and contracts when it gets freezes, except with a few exceptions. Water is very strange. It'll cool, as you cool it down, it gets to about -4 degrees. You see, it starts to expand. Why does it expand? If it didn't, there wouldn't be life on the earth, because lakes would freeze from the bottom up, not from the top down. So when you discover the behavior of water, you discover it behaves a peculiar way to make life possible, and yet when you analyze the curve of its expansion and contraction thing, it's very bizarre. It's been tailored to comply with what man needs, which is evidence for design. But again, we see these nonlinearities. Perhaps the most dramatic in our life is the field of biology. We have been victims for many decades of Darwinian ideas, and evolution, of course, has become the dictum of our schools and our administration and what have you. But it's interesting that there's some, most of you in this audience, I think, are well acquainted with the foolishness that masquerades as the theory of evolution. But let me take it another step. A guy by the name of Bishop Paley first used this example many, many years ago in the 1800s. But he spoke of his watch. If I have this watch and told you that several engineers designed it, carefully tailored it, manufactured it, sold it to a jobber who sold it to a jeweler who sold it to my wife as a gift for me, you'd believe that. But if I said to you, that's not what happened at all. Actually, millions and millions of years ago, there are random atoms floating through the universe that came together to make certain parts that, fell together, and as I unfold that yarn, you laugh because it's so absurd as to be humorous. Yet the watch is an open-loop system, which is the simplest of the systems. The wrist upon which it resides is a closed-loop servo system, far more complicated than the watch. Yet we laugh at the idea of the watch being in existence without a designer, and yet we take for granted, actually the world does, that the wrist upon which it resides happened by chance, which of course is absurd. You've heard that analogy. The whole idea of there's open-loop systems, much more complicated are the closed-loop systems. There's probably not one engineer in 100 that knows what a Nyquist diagram is, how to design a closed-loop system. But even beyond that you have self-modifying systems, self-healing systems, self-reproducing systems. These are all levels of complexity in design. And it's interesting that some of these complexities that we observe are too complicated for us to engineer ourselves, and yet we attribute their existence to the accident of randomness, which of course is so patently absurd as to be ridiculous, and yet that forms the philosophical framework of our world today, obviously absurd. But let me go one step further that most people don't realize. Suppose I went through that same little analogy and pointed out we got a digital watch. I've discovered as I travel and talk to people, most people have no idea of a basic distinction that engineers are aware of, but laymen are not. Most of the world you and I encounter would be classed in the information sense as analog systems. For example, a thermometer on a wall is an analog system. That is, if it's twice as high, it's twice as warm kind of thing. In other words, some physical dimension that's continuous is a replica or an analog of something we're trying to measure. A ruler actually is an analog device because twice as long is twice as long. There's another way of representing information. Not analog, it's called digital. That's where we use symbols. The best example that you're probably familiar with is a clock. A clock with hands is an analog expression of time. As the hands move, you can glance at it and get a feeling for how much time has passed. We also have, as you all experienced, digital watches, where it'll say, 8:15 or 8:15. I don't know if you're like me, it's easier to see an analog display and know what time it is than yet when you see the digital, you have to translate it, so to speak. But the real point is, if I have a digital display, that means I'm representing information by a group of symbols that are arbitrarily defined. There's nothing intrinsic about an 8. There's nothing that makes an 8 intrinsically, a little bit more than a 7. Or more than, in other words, these are arbitrary symbols. They could be a Z or a Q or a P if we previously agreed that they represented. In other words, the idea of digital codes implies language. If I had a blackboard here and wrote M-A-N, you say that means man. Only because we've agreed to that in advance. You happen to know English, so to speak. I could probably pick some clever examples that would mean something quite different in a different language. You follow what I'm saying? Language implies context. The classic example of Paul Revere's ride at the Old North Church, one if by land, two if by sea. Why? Because that's what they agreed the code was, right? Language implies anticipatory design. If you design a computer, you generally have to decide and agree and think through the symbols it's going to manipulate and the language you're going to use to communicate with it. The point is they can't evolve accidentally. Language can't evolve independent of the implementation of that language in a computer sense. If I have a digital watch and I'm looking at a digital watch and it says it's Friday, February 4th, how does it know? It might know when a day goes by, but how does it know that we call this month February? How does it know that it happens to be the 4th day of that calendar? How does it know when it gets to February 28th or 29th to skip over? How does it know that it's, Friday night rather than something else? Because there's a language we've agreed to that's been programmed in. There's no way you could possibly conceive of this watch accidentally coming together and providing me that information. Because how would the watch know our language? You follow what I'm getting at? Now, why am I getting at all this here? Because they've discovered our DNA code. In every cell in your body, there's a DNA. You've all heard about it by now. The DNA code carries a message that tells the cells and what proteins to build to make up you. It's in a digital code. The DNA code is a 3 out of 4 error-correcting code. And I suspect there isn't a computer engineer in 1,000 that even knows how to create a code that's error-correcting. Some do, but it's a specialized art. The DNA molecule has punctuation, start bits, stop bits. It has a 3 out of 4 code that instructs the cells on what sequence to build the proteins that make up you. Your entire genetic history is recorded in the DNA in a digital code. What does that mean? That means it had to be designed. That's why you don't have interspecies discoveries. That's why Darwin is dead. 120 years of searching, they've never found a missing link. Why can't they? Because they're digitally defined. You see, if you got a digit means 7, a digit that's 8, you have no digit means 7.5, unless you further go on to define that somehow digitally. In other words, digital implies discreteness. That's why Genesis says that each after their own kind. You say, well, gee, what's interesting is all living things have the same coding. That's right, it all came from the same software house. And you say, Chuck, I hear all this, but where are you headed? I want to talk to you about nonlinearities tonight. But let me tell you about another nonlinearity that's shattered the field of physics. In fact, most physicists will get violently upset with what I'm about to suggest to you. And what I'm about to suggest to you is conjectural. It's not certain for sure, but it's very provocative. Scientists have, from the beginning of science up to Descartes, really, taken for granted that light was instantaneous or traveled at a very, very high speed. It travels instantaneously. It was through the efforts of Olaf Rømer, a Danish astronomer, who by using the eclipse of Io around the planet Jupiter measured the speed of light for the first time and discovered it was about 300,000 meters per second. For 50 years, the field of science laughed at that. They couldn't absorb the idea that light had a finite speed until a guy by the name of Bradley in England confirmed Rømer's experiment, and that settled it after 50 years of arguing about it. It's interesting how conservative science is, how long it takes for some of these basic ideas to be absorbed. The point is, the speed of light has been measured 143 times in the last 400 years. And an Australian by the name of Barry Setterfield and a mathematician by the name of Trevor Norman, some years ago, decided to analyze the data from all those experiments. And they compiled data from the original experiments from Rømer on. And they discovered something very strange. They discovered that the speed of light, obviously as the years have gone by, the accuracy has improved. Where the accuracy in Rømer's experiment, as I recall, was, I don't have my notes with me, plus or minus 5,000 meters. Now it's 300,000 meters per second plus or minus 5,000. Not bad, really, for that day. Today, with the National Bureau of Standards and lasers and so forth, they can get it down to a very, very small fraction of a meter per second. But the point is, as the years have gone by, the error band gets smaller. But here's the bizarre thing. The median of the data falls outside the previous band. In other words, to make a long story short, it would seem that the speed of light has been slowing down. Now, not by much in recent years, but the implications are staggering as if Setterfield is correct. In fact, not only does it correlates 99% to a cosecant squared curve, which means that not only did it slow down, it's a curve. It's been almost asymptotic, hardly changing at all in recent years. But it means that, extrapolating backwards, the speed of light was incredibly high in ancient times. Now, this has shattering effects on the field of physics, because the field of physics, for a variety of good reasons, has taken for granted that the speed of light is a constant. Einstein mentioned several times in his papers, he's surprised that there'd be any constant in the universe. But he also accepted the speed of light was constant, but surprised that it would be. Now, most classical physicists laugh at Barry Setterfield's thing. They don't buy this at all, and they have all kinds of reasons, but it turns out if you look at those reasons carefully, they fall apart, at least potentially. Over the years, slowly, here and there, certain key scientists are beginning to take Setterfield more seriously. If the speed of light's been slowing down, what that does, it disconnects dynamical time, like the orbit of the Earth or what have you, time measured that way, in an astronomical sense, with atomic time, or the speed of light, and or the distances that light implies. This means that the 15 billion light years of the universe may actually be much closer than we think, because when it was started out, it was going a lot faster. Some of the calculations even suggest that the age of the universe might be less than 10,000 years, just to show how dramatic these things can be. Now, if you're really into this sort of thing, you know that the multiplication of entropy and the speed of light is a constant, which implies that the speed of light's been slowing down, entropy's been increasing. All of this may have started at Genesis chapter 3, when Adam sinned and entropy was introduced. I don't want to make this a study in entropy tonight. I mention that in passing. Whenever I talk about light, I'm reminded of an analogy that Dr. Alex Metherell first showed to me many years ago. And it's a strange analogy, but bear with me as long as you've come with me this far. I don't know how many of you have ever had the chance to see a real hologram. We use the term hologram for these little images on credit cards and stuff. That's really something a little different. A true hologram is an image, a three-dimensional image that's created by, in effect, a laser without lenses. And the example I'll use, I'm wearing a necktie and a suit. If I held my Bible in front of my necktie and you took a photograph of me, you wouldn't be able to tell what kind of necktie I was wearing, because the Bible's in the way. By taking a picture with a camera, you get what is called a two-dimensional image. If, however, instead of that, you decided to try to set up a hologram, what you would do is illuminate me with a laser and put a piece of film, no lenses, just a piece of film, in such a way that on the film falls direct laser light from the laser and also reflected laser light from me. You take that film after proper exposure and you put it through the processing in a darkroom, and what you end up with looks like a darkroom mistake. Looks like a clouded piece of film. Until you illuminate that piece of film with the same laser that we used to create the image in the first place. And something very strange happens. That piece of film looks like a window into a three-dimensional space. The reason it does is what the film has captured isn't the direct reflections, it's recaptured the interference of the light coming, the coherent light from the laser and the reflected light from me, and it records where those things interfere. What the result actually is, it's a Fourier transform of the image. But here's what's interesting about it. If I use the example that I was holding a Bible in front of my necktie, if you moved your eye, and I held this film up, you can move your eye and look around my Bible and see the tie. See, in other words, it's a three-dimensional image. Even though the necktie is behind the Bible, on the hologram, it would capture that. And so holograms have some very peculiar properties. Now, why am I getting into this kind of a strange subject, I guess, except for the following reason. I'm fascinated, I've always been fascinated with light anyway, anybody who's interested in physics would be, but also it's the first direct quote of God in the Bible. Let light be, or let there be light, as it's translated in the King James. It's interesting, there are four basic equations about light, and they all are analogous to the attributes of God. He's at infinity, light's parallel, you got parallelism. I won't go through all that right now without slides and stuff, heck with that. The thing that is interesting is the hologram has some interesting properties that I'd like to call to your attention. If I have the hologram in front of you and I cut a hole, say 1 inch square on the hologram, well, if I took a picture and cut a 1 inch square, you've lost something of the picture, obviously, right? You take a picture and cut a 1 inch square out of it, you've obviously lost whatever was that square. In a hologram, if I cut a 1 inch square, it doesn't hurt you because you can move your eye around the hole to see what it represented. If you cut the hologram in two, you get two complete holograms. They're not quite as sharp as the first one, but you lose no information in the sense that you still see the complete image. You follow what I'm saying? Kind of strange, isn't it? If you take the hologram and hold it in natural light, it looks like a darkroom mistake. It shows no image until you illuminate with the laser that made it. It's kind of interesting to me that we have in our hands 66 books written by 40 authors over thousands of years. It has no form nor comeliness that you should desire it. If you look at the Bible through natural man's eyes, they're a collection of quaint myths and legends and some history, it's disparaged. But if you illuminate this Bible by the light that created it in the first place, you get an image, the image of Jesus Christ. It's interesting that if you take a hologram and cut a piece out of it, you don't lose any information. Why? Because every piece of information in the hologram is distributed over the entire surface. That's why you can cut a piece out of it and not lose it. You may lose a little sharpness, but you don't lose the image. It's interesting that the Bible is organized the same way. You ever notice that there's no chapter on baptism, there's no chapter on salvation? Take any subject, any important subject is distributed throughout the book. Just like a hologram. Tear out a page, tear out a book. The critics have. What's really provocative, if you study the mathematics of this, you discover that the way it's designed, and by the way, Isaiah points this out. This isn't accidental. God says in Isaiah 29, I think it is, he says, I have established my truth line upon line, precept upon precept, here a little, there a little. Why? If you're any communications engineers in the audience, they know why. It's organized exactly the way you'd organize it if you anticipated hostile jamming. If you're designing a communication system in anticipation of adversary jamming, you take your message and you spread it on the available spectrum. That's exactly what the Bible has done. In effect, if I may use a parallel, it's like a Fourier transform of the